black holes. Many say they represent the very boundary of human understanding. True to their name, they are realms of profound darkness, peculiar and shrouded in terrifying mystery. Today, black holes are among the most intently watched objects in our cosmic observations. But did you know that it wasn't until 2019 that humanity finally captured its first real image of one? Before that photograph came into existence, black holes lived only in our theories or within the complex equations of physics. That historic moment changed everything. It was proof. Black holes are real, and everything theorized about them was true. To us, a black hole is an object both terrifying and fascinating, holding within its darkness our deepest yearning to understand the cosmos. So, what do we really know about them? How terrifying are they, truly? Could a human survive an encounter with one? Today, we will journey together to explore the universe's most powerful monster and uncover the grim reality of facing it. As always, don't forget to like and subscribe to support the creators of this content. We hope you have an engaging experience with today's exploration. A black hole is a region of space-time where gravity is so intense that nothing, no particles, not even electromagnetic radiation like light, can escape from it. Einstein's general theory of relativity predicts that a sufficiently compact mass can deform space-time to form a black hole. The boundary surrounding it, from which no escape is possible, is called the event horizon. The term black hole is fitting because it absorbs all light and matter crossing the event horizon, acting like a perfect black body in thermodynamics. Based on their formation and mass, we classify black holes into three primary types: stellar mass black holes, intermediate mass black holes, and supermassive black holes. Stellar mass black holes, weighing about 10 times our Sun's mass, are born from the violent collapse of massive stars. They are the most common type we've detected. Intermediate mass black holes bridge the gap between stellar and supermassive varieties, with masses ranging from thousands to a million solar masses. Their formation remains a topic of active debate among scientists. Supermassive black holes are the universe's heaviest behemoths, weighing millions to billions of times our Sun's mass. They are thought to form through special mechanisms, such as the merging of galaxies or the devouring of other black holes. While by definition a black hole is invisible, a perfect void, we can infer its presence through its violent interaction with surrounding material and light. Matter, spiraling into a black hole, forms an accretion disk. Here, particles collide and generate immense friction, heating into a plasma so bright it can outshine entire galaxies. If a star orbits a black hole, its path and period allow astronomers to calculate the black hole's mass and distance, distinguishing it from other dense objects like neutron stars. Through such methods, we've found many black holes in binary star systems and identified a supermassive one, Sagittarius A*, lurking at our Milky Way's heart, weighing about 4.3 million solar masses. A common misconception is picturing black holes as incredibly dense objects. While they form from immensely dense matter, the black hole itself is nothing. Our Sun has a diameter of about 1.5 million kilometers. But if you could compress the Sun, squeezing it smaller and smaller until it was a sphere merely 6 kilometers across, its colossal mass would force it to collapse further and vanish. There is no surface, no material thing, left only an empty region of distorted space-time. If you approached a black hole, you might not even realize something horrific lay ahead until it was far too late. Imagine you're on a cosmic voyage to visit one. How would that journey unfold? Could you survive and escape? To understand, we must first grasp the concept of curved space-time. In the 20th century, Einstein's equations described how space and time react to matter and energy. If you throw an object near Earth, it follows a curved arc. Throw it fast enough, and it achieves orbit like the International Space Station, traveling at over 28,000 kilometers per hour. It is, In fact, constantly falling around our planet in a perfect curve. These orbits are illustrations of how mass curves the fabric of space itself. So, if you were exploring space and stumbled near a black hole, you might not see it coming. A black hole acts like a cosmic lens, warping the light around it, but instead of focusing it, it bends light into an infinite curve. A phenomenon we'll see later in the first black hole image. Back to your journey. By the time you realize your proximity, it's likely too late. You would be inexorably captured. Even if your ship had unimaginable power, your first insurmountable problem would be fuel. Consider the energy needed just to escape Earth's gravity. A spacecraft must reach about 11.2 kilometers per second. This requires enormous rockets and colossal fuel loads. Now imagine the gravitational grip of an object millions of times heavier than our Sunday. No conceivable amount of fuel could give you the escape velocity needed once within its pull. Survival and escape are not just unlikely, they are impossible. As you draw nearer, time itself warps alongside space. The interval between your heartbeats, your thoughts, slows relative to someone far away. For you, time feels normal, synchronized to the warped frame around the black hole. But to an outside observer, your clock would appear to freeze. This is just the beginning. Eventually, you would cross the point of no return, the event horizon. Once past this boundary, nothing, not even light, can escape. During your approach, you'd experience one of a black hole's most famous effects, spaghettification. Caused by the extreme difference in gravitational pull on your head versus your feet, you and your ship would be stretched into long, thin strands like cosmic pasta, then torn apart at the molecular level. You would cease to exist as recognizable matter. But let's assume, miraculously, you survive this. What awaits deeper in the heart of a black hole is the singularity, a point where density and gravity become infinite, and our known laws of physics break down. Here, the theories of quantum mechanics and general relativity clash, and the fate of matter is unknown. It might vanish, become part of the black hole's structure, or something else entirely. This profound mystery has inspired fascinating theories, like the one depicted in the 2014 film Interstellar. Its scientific consultant, physicist Kip Thorne, suggested that inside a black hole could exist a five-dimensional space. In this bulk, gravity is a fundamental force, and light or sound from our three-dimensional universe cannot penetrate. Some hypotheses even suggest that what falls into a black hole doesn't plunge into the singularity, but hits a two-dimensional surface, a holographic projection of all its information, like a cosmic photocopy. In this bizarre scenario, you might exist on a different plane of reality, utterly deceived into thinking you're still in a familiar, three-dimensional world. It leads to a staggering thought. Could we, right now, already be living inside a black hole? The speculation goes further. Perhaps not just Earth, but our entire universe resides within a black hole. This could help explain the origin of everything. We know the Big Bang occurred about 13.7 billion years ago, initiating a rapid expansion. But what existed before? Some models suggest a singular, infinitely dense point, a singularity that erupted. Interestingly, a black hole also contains a singularity, but instead of exploding outward, it pulls everything inward. What if our universe is inside a black hole that's continually feeding on matter from an external cosmos? The inward flow of material could fuel our universe's expansion from the inside. The largest black hole we know, TONS 618, has an event horizon over 390 billion kilometers wide, 43 times the diameter of our solar system. Yet even this is far too small to contain a universe. But if our universe has a shape like a giant donut, a mathematically possible model, and you can never reach its edge, perhaps the question of containment is a matter of perspective. If each black hole contains a separate universe, reality might be structured like a branching tree of nested cosmic realms. This black hole universe theory could even address other puzzles, like dark energy, the mysterious force accelerating cosmic expansion. Could dark energy be the manifestation of external matter falling into our parent black hole? While such ideas answer some questions, they raise even more profound ones. How could we ever test if we live inside a black hole? That may await future scientific revolutions. Another tantalizing idea is time travel. Near a massive object, time slows down an effect called time dilation. A year near a black hole could equate to decades or centuries back on Earth, as seen in Interstellar. In theory, you could travel to the future by skirting a black hole and returning. Traveling to the past is more complex. The extreme warping of space-time could, in theory, create closed time-like curves loops where you end up in your own past. But to enter and exit such a loop, you'd need to cross the event horizon and then escape, which requires moving faster than light. For now, visiting dinosaurs or future epochs remains firmly in the realm of science fiction. Despite being among the universe's greatest mysteries, our understanding of black holes is still in its infancy. Scientists relentlessly study their nature, using observations of surrounding radiation and advanced simulations to probe these hostile, awe-inspiring environments. However, the day we truly unravel their secrets is not coming soon. It's hard to believe, but after centuries of theorizing, we obtained our first direct image of a black hole only a few years ago. The history of black hole research is an epic saga spanning generations, and that first image is the culmination of countless brilliant minds. The idea of an object so massive that light cannot escape was first proposed in 1783 by John Michel in a letter to Henry Cavendish. In 1796, Pierre-Simon Laplace discussed similar dark stars. The concept was largely forgotten in the 19th century, as light was thought to be massless and unaffected by gravity. Then came Albert Einstein. In 1915, his completed theory of general relativity described how gravity bends light. Shortly after, Karl Schwarzschild found the first exact solution to Einstein's equations, describing the spacetime around a spherical mass. This solution contained the Schwarzschild radius, a critical boundary where spacetime becomes so severely distorted that it forms a black hole. Research accelerated in the mid-23th century with the discovery of pulsars. The work of Stephen Hawking and others in the 1970 seconds gave birth to black hole thermodynamics, linking properties like mass and surface gravity to concepts like temperature and entropy. Hawking's groundbreaking 1974 theory showed that black holes aren't completely black. They emit faint radiation due to quantum effects near the event horizon. The term black hole itself was popularized by physicist John Wheeler in 1967, and it quickly captured the public imagination. The quest for that first image was a monumental, global effort. The picture we see is the result of the Event Horizon Telescope (EHT) project, a virtual Earth-sized telescope created by linking 8 observatories worldwide, involving over 200 researchers. The image shows the supermassive black hole at the core of the galaxy, Messier 87, 55 million light-years away. All previous depictions were artistic renderings or simulations. This was the real shadow of a black hole, cast against the glowing disk of superheated matter swirling around it. The orange-gold ring in the image isn't its true color. It's a color map chosen by scientists to represent intensity. with yellow being the brightest. In reality, the disk likely shines in white light. The central dark void is the black hole's shadow, the closest we can come to photographing the unphotographable. Over time, our knowledge continues to grow. We dare to dream of a future where this cosmic monster is decoded, where mysteries of time, matter, and extra dimensions are laid bare. What do you think? Is the black hole a worthy object for our greatest scientific efforts? Could deciphering its secrets open a new chapter in the history of science? Thank you for joining us on this journey through the cosmos. If you enjoyed this exploration, please like and subscribe. Farewell for now, and we'll see you in the next video. May you have a wonderful day.